Alright, so last class we talked about rotational inertia and kinetic energy, and then you did some problems working that, rotational and kinetic energy. So today we're going to move into torque and how angular acceleration affects your torque, or rather how torque affects your angular acceleration. So to start us off, we're going to start with vectors. So we're going to review vectors very quickly, and then we're going to talk about how we multiply those. So first things first, let's start off with a vector. What's an example of a vector?
Velocity.
So velocity. So velocity is a vector. Why is it a vector?
Because it has direction and magnitude.
Magnitude and direction. So give me a velocity vector.
2 meters per
per
second.
second at 1 degree above north of east.
Okay. So we have 1 meter per second at 1 degree north of east. So it has a magnitude and a direction. So the direction could be written like this. It could simply just be east if it was going straight east. It could be north. If I said northeast, what does that mean?
Oh damn it, 45 degrees.
That means 45 degrees. So that's fine if it's 45 degrees, but if it's not 45 degrees, you can't say northeast. Okay? So I'm going to change this. I'm going to make this real simple. We'll say it's 1 meter per second at, well, let's just say 1 meter per second north. And I'm going to call this vector A. Okay? So I need a second vector, second velocity vector.
4 meters per second east.
4 meters per second east.
1 meter per second south.
Okay, I'm going to call this vector B. So if I have a graph here, where this is north, south, east, and west, if I was to draw my vectors on here, I would have one that's going 4 meters per second east. So this is 4 meters per second. And I have one going north. And this is only 1 meter per second. Okay, so how would I find the resultant? How do I add these two vectors?
Put the tail head to tail.
Head to tail. So I have to come over separately and I'll say, okay, does it matter which one's first?
No.
So I can start with 1 meter per second and go like this. Say this is 1 meter per second north. And then I can add to it 4 meters per second east. And so my resultant is from where I started to where I ended, right? So remember, it's a vector, so it has magnitude and direction. So how do I find the magnitude of this?
The Pythagorean theorem.
Pythagorean theorem, and how do I find the direction?
Tangent.
Yeah, I want to find this little angle right here, right? Tangent inverse, right? So does it matter? So if I go 4 meters per second and then go 1, do I get the same resultant? Yeah, so order doesn't matter in this case, okay? That's how you add two vectors. Y'all remember this? Hopefully you do. So this is vector addition. So vector addition, okay. So I'm going to briefly touch on vector subtraction because we talked about it before, but it's very similar to vector addition. So here what I've done for vector addition is I've added, I took vector A and I added vector B. Okay, and that gave me my resultant, or vector C. However you may say it. Everybody okay there? So what I'm going to do now is I'm going to subtract. So I'm going to take vector A and I'm going to subtract what? Vector B. Okay. So vector A still looks like this, right? Separate this. This is addition. So now we're doing subtraction. So I've got vector A, which is 1 meter per second, right? So I could write negative B, but how would I write negative 4 meters per second?
Flip it.
You know, say I could just draw it going west.
Yeah.
So this is 4 meters per second west, right? So in this case, I can still calculate my resultant here. Still using Pythagorean theorem. And now I want to find my angle. I can always measure your angle from positive x here. So I'd find this theta here and add 90 to it. So if you don't recall us going over vector subtraction, there's a reason, because it's basically just like vector addition, right? I'm just adding a negative b. Everybody recall this stuff? We went over it at the beginning of the year, and hopefully you've been using it, although on your last test some of you did not. So that's vector subtraction. So do y'all have any questions about it? This is just a review of what you know of vectors. Okay. I hear no response.
Can
So-
you also subtract with tail to tail?
You can.
Okay, just making sure.
Alright, so now what I want to do, I'm going to use these same two vectors that I've been using, and I'm going to show you all how to multiply two vectors. Okay? So, to multiply two vectors, there's two basic ways to do it. So, let me stick to my colors. So if I want to take vector A, I'm going to multiply it by vector B. Y'all are familiar with this dot meaning multiplication?
Yes.
Yes. Okay, so the way we do that, we've already done stuff like this before, so this isn't anything new. Sorry, let's stick to the same colors. B. The way you actually do that is you say A times B gives me the magnitude of A, so absolute value sign, because if it's positive and negative, you just get the absolute value, times the magnitude of B, means I don't care about the direction, times the cosine of the angle between them. Okay? And that will give me my resultant, or vector C. I'll just call it vector C in this case. Sorry, not vector C, just C. Okay. Now, this thing is called a dot product. Okay? It's called a dot product because that kind of looks like a dot. So it's magnitude of A times magnitude of B times the cosine of the angle between A and B. So if you look back here at this drawing that I have, what's the angle between vector A and vector B?
90.
It's 90 degrees. So what I want you to do is with your calculators, get your calculator out, and I want you to type in, what would you type in to do A dot B?
1 times 4 times cosine 90.
So we're going to do 1 meter per second times 4 meters per second times cosine of 90. Alright, so y'all physically type that in.
0. No.
Well, 90 degrees. If you want radians, what is that in radians?
Negative 1.7.
That'd be pi over 2. Right. So, it doesn't matter what you're in, but just note, if you're using one of my calculators, it's nice. It says what mode you're in right there on the bottom. So if you're in degree mode, use 90. If you're in radian mode, use pi over 2. So what do you get here?
0.
0. And that's exactly correct. Why do you get 0?
Cosine of 90 is 0.
Yeah, the cosine of 90 is 0, so this should not be surprising that it's 0. Okay? So now you're thinking, what was the point of that? Well, it turns out that the dot product of these two is 0. Okay? Is there a time it won't be 0?
Yeah.
Sure. And you've used this before. Can y'all recall when you've used this before?
No. Yes. Leg times the angle of, it's the Pythagorean, the real Pythagorean.
No, that would be sine and 1/2.
If you've looked up here, work is force times displacement. And so you remember we have to have the force and the displacement in the same direction in order to do work. Y'all remember that? And so we use cosine to get in the same direction. Are these two ever going to be in the same direction? They even have components that are in the same direction.
No.
No, because they're 90 degrees, they don't have any components, so we get no dot product. But we do use the dot product for work, okay? So this is called the dot product. This is one way to multiply two vectors. So this is the dot product, also known as the scalar product. What does the word scalar mean?
No direction.
Yeah, it's just a number. So this number here, whatever you get out of here, it's just a number. It has no direction. Okay, it's the dot product. It gives you a scalar for your answer. Right? So work, what's the unit for work?
Joule.
Joules, it's energy. Is energy a vector?
No.
No, it's just energy. You either have it or you don't. Okay. So the scalar product gives us just a number. There's no direction, no funny business. And we use cosine because we want them to go in the same direction. Remember, you only do work if you push it in the direction it's moving. Does that make sense? If you push it, it moves up. Did you make it move up? Not if you push it to the left. All right? So something else had to have done that work. All right? So another example of the scalar product, which you've already used, is that formula. What's that formula?
Kinetic energy.
For kinetic energy. It's 1/2 mv squared, but velocity is a vector, right? Now, we really didn't mention the cosine of this guy before. Why don't I mention the cosine of it before? What's the cosine of v and v?
0.
Yeah, it's 0 degrees.
Of 1.
So the cosine would be 1. So it's always going to be that because it's the same vector. Does that make sense?
Yeah.
So before we talked about how when you square your vector, you lose your scalar, or you lose your vector information. And that's true because it's a dot product, right? In the end, you get a scalar out. And again, what's the unit for kinetic energy? Joules. And so again, it's just a scalar. It's just a number, okay? So y'all been doing dot product this whole time, and I just didn't tell you. Okay?
Why'd you tell us now?
Because we're about to do something different. Okay, so is everybody okay with the dot product?
Yes.
Okay, and the whole point of this is that we wanted these two vectors in the same direction. Okay, that's why we did cosine. So any questions?
What about divide? What about divide?
We're not doing it.
Okay.
I didn't teach you multiplication when I taught you this. So, take it one piece at a time. We won't do division of vectors this year, no.
No?
No.
It was possible.
But as you can imagine, it's very similar to multiplication.
It was some.
Huh?
No.
Okay. So that is the dot product. So are there any other questions here? Okay, there's a reason why we didn't introduce this stuff at the beginning of the year, because it's all separate. You don't want to just make your brain explode all at the same time. Okay. Okay. So let's talk about this thing here. This is called the cross product, also known as the vector product. Okay, so for the vector product, it says, do it the same way. So cross product, C-R-O-S. Cross product. So when you do this here, you get a vector as your answer, and that's the key difference. They're both multiplication, but this one gives you a scalar and this one gives you a vector. Okay. So when you're doing the cross product, I can use vector A, and I'm multiplying it and crossing it with vector B. Okay. So do y'all see why it's called a cross product?
Yes.
It's got this big X here in the middle. Now what I think is funny is when you learned math for scalar stuff, for scalars, you can do either, you get the same thing. But I bet most of y'all remember when you learned multiplication, they said it was this. And then when you learned algebra, they're like, no, it's really like this.
Yeah.
And you're like, why did we switch? And they told you what?
Because we're lazy.
It means the same thing.
It's faster.
Because you're already using X, right? Or you could say it's faster than writing this, or you're lazy, or whatever. Well, in reality, this is a different thing than this. Okay?
That means hydrogen.
Then for scalars, it really doesn't matter. But for vectors, yeah, that matters. Okay? So really, they wanted you to switch to this because if you have two scalars, really you should just be doing this. And this doesn't make sense in terms of a scalar number. Okay? So if we're doing the cross product, the way you do it is you do the magnitude of A times the magnitude of B, sound familiar?
Yes.
Times the sine of the angle in between. Okay.
Ah.
Now, up there you'll see it doesn't just say sine, it's also got this little guy hanging out there. We'll talk about that little guy in a minute. Okay. And that gives me vector C, okay? But let's focus on this. This looks very familiar, right? A, B. Why did we use cosine here? We wanted these two to do what?
Go in the same direction?
In the same direction. Do we want these two in the same direction?
No,
No, we want them at what type of angle?
they're at proper angles.
Parallel.
We want them at a right angle to each other.
Uh,
Does that make sense?
Yeah.
Okay. So this stuff we want at a right angle, which is why we use sine, right? So now if let's go back and let's do the same thing here. And so y'all type it in your calculator. So in your calculator, let's do A cross B. A cross B. So what do I plug in for A?
1,
1 meter per second. What do I plug in for B?
4,
4. What's the angle?
9.
90 or pi over 2, however you want to do it. And what do you get? 4. Very amazing, right?
Oh, wait.
4 meters per second, okay? Now, so that's easy, right? That's not a big deal, hopefully. So notice that for a dot product, you'll get maximum dot product when they're in the same direction, and for cross product, you get maximum cross product when they're at 90 degrees from each other, right? So now let's talk about this guy. This guy is the direction. Okay, we didn't have the direction over here because this is not a vector anymore. Okay, this is a scalar. This is a vector, so it's got direction to it. So the way you find direction is you use the right-hand rule. So what axis is this?
The X.
X. This is positive X, negative X. This is what? Y, positive Y, and this is negative Y. And there's also a Z axis, which would be in what direction?
Out.
Okay, you'd say positive Z is out of the board, and negative Z would be into the board, okay, for a third dimension. So, y'all bring your right hands with you today? Right. Well, some of you did. Okay. Those of you that didn't, look on with your partner. So you've got your right hand. The way you do this is you take your fingers, point them in the direction of your A vector. What's the direction of my A vector? It's north.
Oh, my hand doesn't
It'd be
work.
positive Y. Y'all see that?
Oh, wait.
It goes up, okay? The second one, B, is the direction your palm points. So if my fingers are going up, what direction is B?
Positive.
Positive, so I gotta go like that. Y'all see that?
Wait.
Wait.
What?
Can we do that again?
I'm gonna call this one positive next.
Is that what you want? Okay. So positive, so I got A is going up, right? My fingers go up. Everybody got that one, right?
And your thumb.
B is where your second one. So the second one's your palm here, right? So I need to point my palm the direction of my B vector. In this case, it's going east, right?
Yeah.
So I go up and I go east. Now, the direction of the cross product is your thumb. And what direction is my thumb going?
That way.
In the
What
board.
direction is that?
Z. Negative Z.
Negative Z. So here my direction is negative Z. So this is 4 meters per second in the negative Z direction. So I can write it like that, or I could just write it as negative 4 Z. Does that make sense? So out of all of this, this is actually not too hard as long as you brought your right hand with you. This should be fairly easy too, but remember there's one way for cosine, or one way for dot product, and one way for cross product. Alright, so I want to show y'all something here. Now, did it matter if I did A dot B or B dot A?
No.
Because if I did 4 times 1 times the cosine of 90, I still get 0, right?
Yeah.
Does it matter if I do 4 times 1 times the sine of 90? Does that change anything here?
No.
No, but does it change anything here? It does. Order matters in cross product. So this is A cross B. So what is B cross A?
Positive Z.
So all of this is still the same. So I still get 4 meters per second, but what direction is it in?
Positive Z.
Yeah, it's just in positive Z because now you start with your first one. So your fingers go in this direction, and my palm goes in the second direction. Do y'all see that? So I've got A, or no. So I've got B, A is up, and so now my thumb comes out of the board. Okay? So as long as you bring your right hand, you should be there. But there's a way to remember this. If you look at this here, if I've got X direction, and I've got Y direction, and I've got Z direction, these are my three directions, right? Positively. So if I start here, if I go X cross Y, what do I get?
Z.
I get Z. So if I do X cross Y, I get Z. Do y'all see that? What do you think I would get if I did Z cross X?
Y.
So if I start with my fingers coming out, Z, my palm goes in the direction of X, I get Y. Do y'all see that?
Oh, yeah, because you do this.
How it goes around like a cycle like this? Is this clockwise or counterclockwise? This is counterclockwise, which is a positive right-hand rule stuff.
Oh my God.
So if I go this way, you get a positive. Can I go Z, Y? Can I cross Z into Y?
Negative.
Yeah, you'll get a negative X. Just like we did Y, this is A cross B, this is Y cross X, I got a negative Z.
That's
So
helpful.
if you go counterclockwise, you get a positive. If you go clockwise, you get a negative here. Alright? So the nice thing is you live in 3 dimensions. This works in 3 dimensions. And if you have 2 dimensions, you'll get a third vector that's pointing straight at the board. Now there's some math I'm not going into all the details. You can read that in your book, or just wait for your math class to catch up. Alright? But these are the different ways, right now, that you should be able to deal with vectors. We have addition and subtraction, and we've got the dot product and the cross product. So now the question is we've already been doing this, and I didn't even bring it up when we started doing this, okay? The thing is we're about to change, okay? Because as examples of the cross product is torque. Another example of the cross product is angular momentum. Okay, and we're about to start learning these things. As a matter of fact, today we're starting with torque. So speaking of torque, its symbol is actually not a T. The torque symbol is actually the Greek letter tau. So it's like pi, except instead of 2 legs, it's only got 1. Y'all see that? So this is the Greek letter tau. It's their symbol for torque. And the way we calculate torque is it's your displacement, in this case we call it R, cross with your force. So remember, order matters. So it's A cross B, right? So your fingers would go in the direction of R, your palm points in the direction of your force, and your thumb will be the direction of the torque,
What
right?
does R stand for?
Your displacement, your radial distance from your point of rotation. And so we're going to get into all this just right now. So what's the unit for a distance?
Meters.
Meters. What's the unit for a force?
Joules. Oh, no, newtons.
Newtons. So newtons times meters, that gives us the torque unit of Newton meters. Now this is the units in SI units. Unit for torque is Newton meters. What's the unit for torque in this country?
Twisties.
What? Twisty, not twisty. Somebody said it's pound foot. Pound feet. Pounds is your force. Feet is your distance.
Who does?
This country does.
No, they don't.
On all the commercials, like, oh, buy the Toyota Tundra, got 400 horsepower and 500 pound-feet of torque.
No way.
I don't know how else to do that.
Can we
Wow.
please not America?
Is it actually?
Okay, so we've got torque, okay? And I'm not going to go into angular momentum right now, but just be aware it's coming, okay? So this is why we started talking about the cross product, because earlier I told you about work. Work is force dotted with your displacement. What's the unit for force?
Joules.
Still newtons. What's
Oh,
the
wait,
unit
I
for
mean,
displacement?
Meters.
Meters. Well, what's the unit for work?
Joules.
It's a joule.
Joule.
Okay? Because these are in the same direction, You can get a joule. These are 90 degrees to each other, so you don't get joules, you get Newton meters. Okay? All right. So any questions right now?
Do you want me to stop this and then start over again on torque?